Ever wonder why your electricity bill can spike by 20% overnight? Or why energy prices feel like a roller coaster? It's not just about the weather or your thermostat. It's a high-stakes game of prediction played by scientists and traders across Europe. Today, we're diving into a groundbreaking study that's rewriting the rules of this game. Here's the key. Electricity isn't like ordering a pizza. It's a real-time balancing act between supply and demand, and prices can swing wildly depending on when you buy it. In Europe, most countries use day-ahead markets, where prices are set the day before. But here's the twist. Each country has its own deadline for submitting bids. Germany and Luxembourg close at 10:15 a.m., while Belgium closes at noon. That gap. It's a golden opportunity. Imagine you're trying to predict the weather. If you get a forecast from a neighboring town an hour earlier, you can adjust your plans. That's exactly what this study did. By using price data from faster-closing markets, like Germany, to predict prices in slower ones, like Belgium, they boosted accuracy by 22% in Belgium and 9% in Sweden. That's like turning a shaky 70% guess into a confident 85%. A huge deal in a world where even small improvements save millions. So how did they do it? They used two powerful tools. The first, called LEAR, is like a supercharged spreadsheet. It analyzes past prices, weather, and demand, filtering out the noise. The second, a deep neural network, DNN, is an AI that spots patterns even humans might miss, like how a heatwave in Germany can send prices plummeting in Belgium. Together, they acted like a team of detectives, piecing together clues from different markets. Here's the kicker. The models didn't just guess prices, they learned from extremes. During a heatwave or a power shortage, the AI could predict wild swings better than traditional methods. But there's a catch. These models need constant updates, which uses a lot of computing power. And more data isn't always better. Sometimes, adding too many sources confuse the AI instead of helping it. So why does this matter? For businesses, better forecasts mean they can plan energy use smarter, saving money. For traders, it's a tool to avoid big losses. And for policymakers, it shows how interconnected markets can stabilize prices, but also how rules like gate closure times create hidden advantages. Next time you hear about electricity prices, remember, behind the scenes, scientists are using AI and smart data to make those predictions more accurate. And in a world where renewables and demand are changing fast, that's more important than ever. But here's another question. How do scientists know if their results are real or just a lucky accident? Let's talk about a super important tool they use, the p-value. Think of it as a detective's magnifying glass for data. Imagine you're testing a new gadget that claims to save energy. You run an experiment, and the numbers show a slight improvement. But here's the catch. How do you know that tiny change is actually because of the gadget or just random chance? That's where the p-value steps in. It's a number between 0 and 1 that answers this question. If there was no real effect, what's the chance we'd see results like these? A p-value below 0.05, that's 5%, is like a red flag saying, hey, this probably isn't a coincidence. Scientists call this statistically significant, meaning the effect is likely real. But here's the thing. If the p-value is higher than 0.05, it doesn't mean the gadget doesn't work. It just means the evidence isn't strong enough to say for sure. What's the null hypothesis anyway? Picture it as the default rule. Nothing's going on here. So if your experiment can't beat that baseline, you don't reject the null. But that's not the same as proving the null is true. It's like a courtroom. The defendant is innocent until proven guilty. If the evidence is shaky, the jury can't convict, but that doesn't mean the person is innocent. It just means the case isn't solid. This matters in energy research all the time. Let's say scientists are studying how solar power affects grid stability. If their data shows a weak link with a high p-value, they can't confidently say the connection exists. But that doesn't mean the link is impossible. It just means they need more data, better tools, or a fresh angle. So next time you hear about a study on energy markets or climate trends, remember, a high p-value isn't a dead end. It's a nudge to ask better questions, gather more evidence, and keep exploring. After all, science isn't about final answers. It's about getting closer to the truth, one question at a time. Ready to see how these stats shape real energy decisions? Let's uncover the next piece of the puzzle.